Let me share with you two stories about conditional probability and how the misunderstanding of conditional probability have a problem in the understanding of real life. The story number one is about the four-daughter family. Four-daughter family. Alright, so how many of you have three other sisters? Like you are coming from a family with four daughters. I don't think any one of you have three sisters, right? If you do, please tell me. But otherwise, it's quite unlikely to come from a four-daughter family, isn't it? So let's see how unlikely or how likely it is, all right? So suppose carrying a boy or a girl has the same chance. So having all daughters families, all of them they are girls, will be, the first girl, the chance will be 1/2, right? The second girl will be another 1/2, and so on. Right, so the chance of a four-daughter family is 1/16, right? So this is it, simple calculation. Now, but let's look at real life. Let's look at real life. I think we have more than 16 students in the class, right? But does any one of you come from a four-daughter family? I doubt it, all right? Even if you look across the whole year, the whole form, all right, there are almost 100 families in the whole form, more than that. How many of them comes from a four-daughter family? Maybe just one, or maybe even no, 0, right? But what is the meaning of 1/16? 1/16 means 1/16. If there are 16 families, one of them should be the four-daughter family. Is it the way how I understand it? 1/16 means that out of 16 families, one of them should be a four-daughter family. But why do we not observe such a frequency in real life? In real life, the chance of running into someone coming from a four-daughter family is much less than 1/16 in our real life. Right? Why is it that so? And then let's look at the other story before we share you the answer. Right? The story number 2. Right, is about community health. For example, there's a rampaging virus. Right, they started an epidemic. Now, the doctors, the pharmaceutical companies, they make a very accurate test, a 99% accurate test. All right, to test whether a person is infected by the virus or not. So let me put it in perspective. What is the 99% accurate test? It means that a person with the virus, all right, a sick person infected with the virus will be 99% chance tested positive, all right, but there will be misdiagnosis, right? There is a 1% chance which will be tested negative. This is what we call the false negatives, all right. He or she does have the virus, but due to the inaccuracy of the test, so it comes up positive. On the other hand, if a healthy person, all right, undergoes the test, 99% chance of the test, it will come up negative for the virus, all right? But there's a 1% chance this will be showed up positive, all right? We call them false positive, these cases. False positives, all right? So that is the meaning of a 99% accurate test. 99% accurate test. Now, a certain person, a certain John, all right? There is a person, John. She joined the test program, and he joined the test program, right? And unfortunately, he is tested positive. All right, he is tested positive. All right, so unfortunate, right? So the question is, what is the percentage chance that John is infected? What is the probability that he actually gets the virus? All right, now let me recap the situation. Now I have a 99% accurate test. A sick person comes in, 99% will be tested positive. A healthy person comes in, 99% will be tested negative. All right, so a certain person comes in, the patient comes in, and we test her. She turns out to be positive in the test. All right, so the question is, how likely is she affected by the virus? Now, most will think it is a stupid question. Under a 99% chance, under a 99% accurate test, if the person is tested positive, of course there is a 99% chance that he is affected by the virus. Am I right? It is a 99% accurate test after all. If he is found positive, all right, what are some other possible numbers he is not affected by the virus? I mean in terms of percentage, other than 99%, right? What are other possible values other than 99%? All right, so these are the two stories, right? And there are two paradoxes coming from the story. Number one, by calculation, the four-daughter family is 1 out of 16, one family out of every 16 family. But in real life, we observe much smaller value than this one, all right? At least in the class, more than 20 students, no one is coming from a four-daughter family, I guess. The second is I have a 99% accurate test. A patient comes in, tested positive. The question is, it seems a silly question, right? Why do we have to ask this? The question is what is the probability that he is infected by the virus, right? It seems that it must be 99%. Right, let me tell you the answer to both stories. In story number one, the 1 over 16 is not the percent of four-daughter family. All right, 1 over 16 is the percent of four-daughter family given there are 4 children in the family, given a 4-child family. All right, 1 over 16, when you do this calculation, there is a hidden given condition, there's a hidden assumption that there are 4 children in the family. All right, there are 4 children in the family. If we have collect all the 4-child family and look at the gender of the siblings, we discover that, well, among the 4-child family, 1 out of 16 will have 4 girls, 4 daughters. That is correct. All right. If you use the Bayes theorem, we discover that that is the probability of having 4 child, and for all of them, they are all girls. Divide by the probability that it is a 4-child family. All right. Now, in real life, we observe 4-daughter family. They're so rare, not because this 1 over 16. It is because a 4-child family nowadays in our society is very rare. All right, it's not very frequent that we have 4 siblings under the same family. All right, so because that number is small, so the chance of meeting a 4-daughter family in real life is even smaller. All right. In story 1, we know that the 4-daughter family, we know that the probability of a 4-daughter family is not 1 out of 16. Before you do that calculation, you have to assume that she comes from a 4-child family. All right, it is among the 4-child family that 1 out of 16 will have 4 daughters, but not just 4 daughters family in general. It goes back all the way to the umbrella and rainy day example. All right, the probability of an umbrella and the probability of umbrella on a rainy day. Rainy day is relatively rare. All right, so it's normally don't find people with an umbrella, but on rainy day there are many people with an umbrella. All right. So this is the idea in the first story. We want to distinguish between PA against PA given B. Right. Sometimes what the tricky thing is, the idea of the given probability is hidden in our daily life language, in the daily life context. So that is the lesson we learned in the first story. All right. Now, how about the second story? Now, I think the best way is to put it in numbers. Suppose we have 1 million people in the entire society. All right. Now, the virus does not affect everyone, right? Only, in fact, only 1,000 of the people, they have contact with the virus. We don't know who they are, all right? But we suspect like 1,000 of them. So the remaining 999,000, they are healthy. They don't have the virus, all right? So suppose we take all these 1 million people to the test. Now, remember, the percent is 99% accurate, all right? So the sick people will be tested positive 99%, but 1% will be the false negative. All right. So how much is that? There will be like 10 people and 990 in this area. All right, this 1,000 people with the virus, we take them to the test. 99% of them, there are 990, will be found positive. All right, we do the similar thing for the healthy people. All right, now for the healthy people, 99% of the chance will be found negative. And how many is that? That is 989,010, right? So many persons will be found negative if they are healthy. All right, but then there is 1% false positive. All right, and that 1% will be 9,990. Am I right? All right, so this is it. All right, if you take all the 1 million people to the test, they will have this result. Now that particular person, let's call him John. All right, John undergoes the test, and he is found positive. What does that mean? That means John is among these two groups of people. All right, we don't know whether. Remember, we don't know whether John is infected or not. We only know that John, after the test, is found positive. That means John may be someone coming out from these 990, or John may be the one coming out from these 9,990. All right, so the probability of John being infected with the virus, given that the test is positive, right? Given that he is tested positive, the chance of having the virus will be 990, both positive and infected. All right, divide by the probability, by the chance that he is actually found positive, right? This should be 990 out of 1 million person. All right, that is the probability that he is one of the person who is infected and also found positive, right? That is the Bayes theorem. Probability of infected and tested positive will be the probability of infected and tested positive divided by just those tested positive. All right, and then for those tested positive will be 990 plus 9,990 divided by 1 million. All right, it is the same 1 million in denominator. So the answer goes to, it's very small indeed. It's only 9%. All right, so if you are John, you don't have to worry about this. All right, even though it is a 99% accurate test, but now you know, because there are quite a number of false positives compared to the true positives. All right, so even though if John is tested positive, it is only a 9% chance that he is actually infected with the virus. All right, in this story, we want to contrast between these two ideas, that if the person is infected, the chance that he is tested positive will be 99%, right? This is what the pharmaceutical companies, they worries about. They want to make very good tests so that a sick person will be tested positive very accurately. But then as a citizen, as a lay person, we worry about the reverse. We worry about if the community member, someone near you, or if yourself is being tested positive, what is the probability of that you are actually infected? In this case, it's only about 9%. It's nowhere near the original 99%. All right. Okay, so try to distinguish between these two ideas, PA given B and PB given A. Sometimes they can differ by very much. And unfortunately, in our daily life, we often mistook these two ideas and say that, oh, if the test is 99% accurate, and then you are found positive in the test, so there is a 99% chance you are infected. But if you understand something about conditional probability, you know that that is not the case, right? As you can illustrate, as you can see in this example. All right, so try to go into the real life and think about more cases that you can apply the idea of conditional probability.